Hello ladies and gentlemen, welcome to our calculus AB and BC session. We're gonna be looking at optimization problems today. Well, at this point, if you are an AP student, I would suggest you go ahead, pause the video, try it before we move on. So here we have the problem 1. We want to construct a box of a square base and we only have 10 square meters of material to use in construction of the box. Assuming that all the material is used in the construction process, determine the maximum volume that the box can have. The very first thing that we need to do here is to consider the area, the maximum volume. The box is going to have a square base. So let's go ahead and illustrate this. The base is a square. So basically this is going to be the height of the box. So let's go ahead and try to finish sketching it. The total area we obtain is 2x squared plus 4xy. Let's remember the formula of the volume, which will give us the area of the base, in this case which is x times the height, which is y. Now let's rewrite down of the area that we found earlier, and if you remember very well, the area, the constraint that we had from here is 10. Can you see some similarities? Yes, I definitely can. In here, if you notice, we have xy here and we do have xy here. How about we pull xy from this formula and replace it in the volume formula? Let's try that. So xy is 5/2 minus x squared over 2, which will lead us to v equals to x into factor. Instead of writing xy, we're going to write the whole value of xy, which is 5/2 minus x squared over 2. Since we have the volume in terms of x alone, we need to take derivative of the volume and equate it to 0 in order to find the local maximum of the volume. X squared is going to give us 5/3, and since distance cannot be negative, we're going to have x, which is root square of 5/3. Now we know the value of x and y in terms of the area. We could always plug it inside the volume, the formula of the area, to find what is the value of y. But before we do that, let's verify whether our local maximum is truly the maximum value of the volume. In order to do that, we can either do that by the table of variation of the function of the volume, or to take the second derivative of the volume, and if the second derivative gives us a positive number at x is equal to root square of 5/3, which means we have a local minimum. In this case, which is not really good for us, we are looking for the case where the second derivative is going to give us a negative number at the point where x is equal to root square of 5/3, which means we will have a local maximum of the volume at the point where x is equal to root square of 5/3. Let's go ahead and try that. So here we have the derivative of the function. So this is the derivative of the function. We're gonna take the second derivative of it. We're gonna have minus 3 root square of 5/3, which is less than 0. Our second derivative at that point is less than 0. Checked. So x is equal to root square 5/3 is the value we've been looking for. So now that we have checked the volume is at its maximum value at the point where x is equal to root square of 5/3, we're going to go ahead and replace the value of x in the formula of the volume that we found earlier. We're going to have, so the maximum value is going to be approximately 2.3942 meter cube. All right.